So today I will talk about congruent and similar figures in solid. If you want, you can print the sheet congruent similar notes, and after watching the video you can practice using the sheet congruent similar practice and answer. When we talk about congruent and similar figure, you have to think about transformation. So we can do two types of transformation, isometries or dilatation. Isometries will move the same figure. Iso means same and metry means measure. So when we move the same figures, we're going to have the same angle measures and we're going to have the same size measures as well. We can check the corresponding sides. Corresponding sides means they're at the same place. So if I look in red here at the hypotenuse, if I do a flip or a reflection, it's going to still be the same length. If I do a turn or a rotation, it's still going to be the same place as well, the same length, the hypotenuse. Or if I just slide it down and I do a translation, it's going to be the same thing. Where if we do a dilatation, we're going to enlarge or reduce the figures. They will still keep the same angle measures, but their corresponding sides will be proportional. What does it mean is that if you look at the hypotenuse here, if I do a reduction, let's say by 2, it's going to be 2 times smaller. The other side here will also be 2 times smaller, and the last side will be 2 times smaller. If you remember how to do dilatation, we would do the corresponding vertex. We will join them with a line, and where all the lines meet, it would be our dilatation point. It's a little messy here on my picture, but you see that if I was doing it more precisely, you would find one point where they all meet, and that would be our dilatation point here. Okay, and we could find our scale factor. We could measure I could measure the side here over the side here, and it's probably 1/2. So my scale factor would be 1/2. Where if I make an enlargement, I would make it bigger. Okay, if you join your points here, you would find that it's getting bigger. Here, okay, where they meet, it's about 2 times bigger. So the ratio or the scale factor, okay, what you need to remember is that we're going to use the length of the image segment over the length of the initial segment. If it's positive, that means they're on the same side of the initial point, the fixed point. If it's positive, or if it's negative, they're opposite side. So if you remember here, if you look at this one, for example, this one here, if we do a negative reduction, it's going to be here on the opposite side. Okay. If you remember proportion, okay, if you remember when we did proportion, we did A over B is equal to C over D. Do you remember what we could do with that? We said we can do A times D is equal to B times C, right? So if we have here the ratio, we're going to call it K, I think, in the book, right? Okay, so the ratio is the image over the initial. So if we put our ratio over 1 and then we do our proportion, then we realize that our image, if I want to find the image, I'm going to put it equal to the ratio times my initial figure. And we'll see what it means when we have numbers. Okay, I just realized I'm missing an I. So if I want to find my image, I'm going to take my ratio times my initial measure. Let's look at some examples. Okay, so for example here, you have two figures. What is the scale factor? They're not telling us if we're going from shape 1 to shape 2 or the other way around, right? So I'm going to use it that way. That's going to give me a scale factor. So let's say my initial here is number 1, and I'm going to my image here. Okay, so to find my scale factor, I need to find my corresponding side first. Okay, so let's look at the short side. On the other picture, it's here. So if I want to find my scale factor or my ratio, I'm going to need to take 3 over 2. That's my K. Okay, if you're going around, if you're going from 2 to 1, then your scale factor is going to be 2 over 3. Now, if you want to write a proportion with this, because what we're doing, we're looking for x here, okay? So we're looking for a proportion. I can write 3 over 2 as to be equal to x over 4, because I'm taking the corresponding side. I'm just going to show you my longest side here corresponds to this longest side here. So what I did, I did 3 over 2 is equal to x over 4. Question 2, they're asking us to find x. So if you remember what we can do, let me put it here. 2 times x is equal to 3 times 4. So 2x is equal to 3 times 4. So I'm going to continue here. So 2x has to be equal to 12. How do we find x alone? 2x means 2 times x. So we need to do the opposite. We're going to divide on each side. So that means our x is equal to 6. Look at question 2. Okay, you have again to find your x. The first thing you should do is find your corresponding side. So the way I do it, in a triangle, there's always a small, medium, and long side. So if I look at the small side, here, this is my short side. If I look in the other triangle, the short side, it looks like it's this one. So short with short, medium with medium, and large with large. And then after you can write your proportions. So you can find your ratio if you want, or you can just write proportions. So I can write 1.2 over y. And now I need to find 2 that I know. I'm going to take the yellow one. So I did 1.2 over y has to be equal to 4 over 6. And then you do your I call it the peanut method. 4y is equal to 6 times 1.2. If you take your calculator and you do 6 times 1.2, you get 7.2. And to get your y, you're going to need to divide by 4, divide by 4. So your y has to be equal to 1.8. To do x, you would do the same. You would do a proportion. Now make sure you're doing it in the same way. So if I'm doing here, I did small triangle over big triangle. So I'm going to do the same. Small triangle, I have x. Corresponding side is 2.4. And I'm doing it with the numbers I know. I know 4 over 6. So again, peanut method, I know 6x is equal to 2.4 times 4. So 2.4 times 4. And then you divide by 6 to get your answer. X is equal to, so 2.4 times 4, that's 9.6. Divided by 6, you get 1.6. Okay. A different type of question you can have is true or false. If you look at this, oh sorry, number 4, let's look at this. If you have a triangle that has a scale factor of 3 over 2, 3 over 2 is the same as 1.5. Is it going to get a shape that's bigger or smaller? So I'm taking this and I need to do times my scale factor. So it's more than 1, it's going to be bigger. Now I need to find what are the dimensions of the image. So I can write A prime C prime. That's my image. It's going to be 8 times 1.5. If you do 8 times 1.5, you get 12. So that means the bigger triangle would be 12 triangles on the, sorry, 12 centimeters on the top. The other side, B prime, C prime. B prime, C prime is going to be 10 times 1.5. It's 10 times 1.5. Take your calculator if you're not sure. 15. So my bigger triangle here, I have 12 here and 15 here. And I'm looking for this one, the other side. So that's, sorry, that's A prime, C prime, and B prime. How can I figure out my other side? I can just use the Pythagorean theorem. I'm going to call it x. Okay, so x squared plus 12 squared has to equal 15 squared. So if I have plus 12 here, I'm going to minus 12 squared on both sides. I'm going to have x squared is equal to 15 squared. That's 225. Minus 12 squared, that's 144. And so 225 minus 144. And then, so that's 81. Sorry, I'm just going to continue here. So I have x squared is equal to 81. Square root on both sides. X is equal to, it would be plus or minus 9, but the minus is not possible because it's a side, right? So the side A prime, B prime is equal to 9 centimeters. True or false? Two squares are always similar. Do they have the same angles? Yes. Do the sides get bigger, smaller? Yes. So that would be, for this one, it would be true. Two rectangles are always similar. Do they always have the same angles? Yes. Do they always have the sides that are proportional? No. Okay, I'm going to show you an example here. If you have a rectangle like this and a rectangle, let's say like this. So do they look similar? Maybe this one is 4 times bigger, but the other one maybe is just 2 times bigger. So it's not working. Two circles are always similar. It would be true. Two isosceles triangles are always similar. Do they always have the same angles? Not necessarily, yeah. So this one would be false. And two equilateral triangles are always similar. Do they always have the same angles, the equilateral? They do. Okay, so this one is true. Now when we do it with solids, okay, solids, they're in 3D, right? So when we have, for example, if we have here something that's 10 by 10, right? If I double it, I double the sides and I have something here that's 20 by 20, right? So my K is equal to 2. What happened to the area? Inside here, the area would be 100. But here, what is the area? 20 times 20. That's 400. How come? Well, this side here is twice bigger, but this side here also is twice bigger. So then your K squared is going to be equal to 4. When we do the area, it's going to be 4 times bigger, the area here. Okay, so the side we do times 2, but the area we do times 2 squared, which is 4. And if we did a solid, if we did a cube, if we did a cube here, okay, the volume of this cube would be 10 times 10 times 10, right? Which would be 1000. If you double hit W cube beside here, it would be 20 times 20 times 20. So you can try it. What's 20 times 20 times 20? It would be 8000. So the volume, it would be K cube. It's the same as 2 times 2 times 2, or 2 cube. The scale factor would be 8. You can see that it's 8 times bigger. So when we do a problem with this, okay, so you have the height of the cylinder. So first you should draw it. So you have a cylinder that's 10 centimeter and that has a diameter of 12. Okay, so there's a diameter of 12 and a height of 10. Okay, and you have a second one that has a height of 4, so it's smaller. It has a height of 4. Okay, and they're asking for the radius here of the small one. What's the radius of the big one? Well, if the diameter is 12, we need to divide by 2 to get the radius. So the radius here is 6. And here we have a height of 10. Here we had the height of 4, and we're looking here for the radius of this one. So we can do a proportion if we want. We can do large over small, just because that's the way they're presented. So large, you have a height of 10 over a height of 4, and it has to be equal to a radius of 6 over a radius of the small. I'm going to write radius of the small. So what do we do when you're here? Okay, we can do our peanut method. We can say 10 times the radius of S is equal to 4 times 6. 10 times our radius is equal to 24. How do we get our radius? We divide by 10 on both sides. So we get a radius of 2.4. Don't forget your unit, centimeters. What's the ratio of the volume of the large one to the one of the small one? So if we're looking at this question here, well, we know K, or ratio, it's 10 over 4, right? It's like the side of the big one over the side of the small one. So that's the same as 2.5. So what's the ratio of the volume? We know the ratio of the volume is K cube. So it's going to be 2.5 cube. So K cube is going to be equal to 15.625. Make sure you're following the order. If they want you to go volume of the large to the small, you have to make sure here you put the side of the large first. Okay. If we're practicing again with ratios, consider the two similar cones on the right. Find the ratio of similarity, the ratio of area, the ratio of volume. So first, I'm going to write here that I'm going to decide that this here is my initial figure. Okay. I'm going to put this in blue. Okay, so this, I'm going to say this is my initial figure, or not figure, but solid. And, oops. I'm going to take that again, blue, and I'm going to call this one my image. Okay, so when we find the ratio, you have to remember that we always do, I'm going to write it here. Our K is always equal to image over initial. Okay, so that's important that you remember that. So when we're going to try here To do the ratio of similarity, we're going to do K is equal to image. We're going to take 4.5 over 3. If you take your calculator and you want to figure out, you'll see that you get 1.5. It's a precise value. You can leave it like that. What's the ratio of the area? I'm going to do it here. The ratio of the area is K squared. So I'm going to take 1.5, but I'm going to square it. Okay, maybe some of you wanted to leave it as a fraction. 3 over 2 is the same as 1.5. So you can also leave it as a fraction if you want, 3 over 2 squared. So if you do it in decimal, you would get 2.25. If you do it as a fraction, it's the same, you would get 9 over 4. And what would be the ratio of the volume? That's K cube. So we're going to take our 1.5, but we're going to cube it. So 1.5 exponent 3, we would get 3.375. If you leave it as a fraction, you have 3 over 2 exponent 3. 3 exponent 3 is 27 over 2 exponent 3, that's 8. Okay. One more problem before we finish that part. You have two cylinders, they're similar. What's the volume of the second one? So first, I suggest you identify your solids. So this is your initial. This here is your initial. This is your image. Okay. So how do you find the volume of the second one? What are they giving you? They're giving you the area. So what can you do if you have the area of each? You can certainly find the ratio of area. Ratio of areas. Okay, that would be equal to our K squared. And that would be equal to 100 pi over, I'm gonna have to take my pen. Okay, 100 pi over 25 pi. How do you get K? Because this is K squared, right? So I want to just take K. I need to square root. Okay, square root. Oh, you see I have pi here and pi here. They can simplify, these two. And I need to square root 100 over 25. What's square root of 100? 10. And square root of 25 is 5. So 10 over 5 is 2. So really my K is 2. Okay. So if you want to find the ratio of volume, you're going to do K cube 2 exponent 3. That's 8. That means if I find the volume of the first one, to go to the other one, I'm going to need to times by 8. So I can find the volume of the initial. How do you find the volume of a cylinder? You do the area of the base times the height. The area of the base here, we know it's 25 pi, times the height is 3. So you can do 25 times 3, that's 75 pi. So if you want to find the volume of the image, the volume of the image is equal to volume of initial times the ratio of volumes, right? So you're going to do, so you're going to do your volume of initial, which was 75 pi, times your ratio of volumes, that was 8. If you do 75 times 8, you get 600. So you can leave it like that, 600 pi centimeter cube. Okay, I know some of you will probably take the calculator and calculate what is 600 times pi. If you want to do that, you're gonna get something that's not precise. You're gonna get 1884.95 dot dot dot. Okay, so it's always better to keep the answer that is more precise. So I would leave it like that, 600 pi. So now you can go and practice. So if you have questions, you can come back in class and ask your questions. Have fun!